All right, let's get all bubbly today. As in, I mean, you know, I always try to be bubbly, but we're going to talk about convection eventually. But before that, radiative diffusion. So we've had our count them, three equations so far for static stellar structure, hydrostatic equilibrium, which we could actually leave leave it in there in terms of gravity not balancing pressure and put in the acceleration term. And then energy generation and mass conservation, mass continuity. Why? Now let's talk about the equation for the temperature gradient. That's the fourth and final of our differential equations, and it's the most complicated of them. That's the one where I'm not going to have you try to drive that on the final exam, because we're going to have a lot to say about that. It's just too long for that. So I don't want to oversell it in terms of like, oh my God, it's scary or anything, but there's a lot behind this one. It'll be good practice with thermodynamics and good stuff like that. So, temperature gradient. Tucked my pants in too well. Temperature gradient. In other words, we want an equation that tells us dTdr in the star, how fast temperature changes with distance from the center. So, why? How can energy be transported? Energy can be transported inside a star by one of three means. That's true not just in stars. Energy can be transported in a star via conduction, convection, or radiative diffusion. So, you know, convection's how a radiator heats a room. We'll have a lot to say about that in a bit. Radiative diffusion, we've mentioned before that more photons are flowing out than flowing in within any given radius, for any given radius of the star, because it's hotter towards the center and cooler towards the outside. We'll talk about that in some mathematical detail shortly. Then there's also conduction, which usually isn't important. Thermal conduction is not important in most stars. Can anybody think of an example of thermal conduction? Do you know what thermal conduction is? What would be an everyday example of thermal conduction? Transport of thermal energy via what we call conduction. So if you put, you got a stove, let's turn on the burner and let's put a frying pan on there, and we're bored, so let's keep our hand on the handle of the frying pan. Will a problem eventually develop? Yes, it will. You'd be like, what's burning? Ah, right, you know, that's thermal conduction. That's thermal conduction. It's like transported. It's more efficient in solids and liquids, which is why it's typically not so important in a star, because they're big gas blobs. That said, it's important inside of a white dwarf, for example, or a neutron star, which are very hot and dense. But thermal conduction is not important in most stars, is unimportant in most stars. But the other two are, under various conditions. And so those are the ones that we're going to be concentrating on. And we're going to first just assume that radiative diffusion transports the energy and find an expression for the temperature gradient in that case. And then we'll tackle the more complicated case of convection. First, we'll assume that radiative diffusion transports the energy. And then we'll find the conditions under which convection dominates. It's an interesting story, I think. Then we'll find the conditions under which convection dominates, and it'll be good. I don't know if it'll be probably a review of some thermal physics there. The conditions under which convection dominates. So finding dTdr in the first case of radiative diffusion is not too bad. We'll have that in a few lines, and then we're going to spend the rest of the time probably talking about the condition for convection. Okay, what questions do you have at this point? Let's do this. Okay, so earlier, if you dig into the notes or in the text, earlier we found the following. We found that dP radiative, the derivative of the radiative pressure gradient, is equal to minus kappa bar, or also mean opacity, times rho, divided by the speed of light, times F rad, which remember is the net flux, the net outward flux carried by radiation. And so we're going to use this as our starting point here. And again, this would be like, oh yeah, right, I got to remember this here. Visiting some old friends here. The radiative pressure, that's equal to 1/3 AT to the 4th power. Let's see, does anybody remember what does AT to the 4th power by itself represent? A is the radiation constant. We've met before sigma T to the 4th power for the outward flux, right? What were we doing when we figured out, the flux is the energy per second per unit area, but then there's something else we wanted to find out. What is that other thing we were trying to find out that also depends on temperature to the 4th power? You're just not spending your spare time reviewing? What's that?
Is it specific intensity? Or just
No, not specific intensity. Nope, not that. This would be integrated over wavelength we're talking about. What are the things we might be interested in? We might be interested in how much energy is being radiated from some surface, but what else might we be interested in about the radiation field?
how much goes into it?
Well, we could do that too, but that's not what I'm looking for quite here. If I have a box filled with radiation, what might I want to do? What might I want to know to figure out what's the total amount of energy in the form of radiation inside that box? What sorts of things might I want to know about that? Assuming it's thermal radiation, it's black body radiation, what would I need to know to figure out how much total energy is inside that box in form of radiation.
How much is radiating and the size of the box?
So we need the size of the box. Size of the box suggests we want to know the what of the box. By the size, what's going to be relevant to find out how much energy is inside the box? You need to know the box's volume. You need to know its volume. And if you knew its volume, what would you need to know about the radiation to figure out how much total energy is in the form of radiation in there? I already know the volume. What else do I need?
The density?
Yeah, the density of the radiation density. AT to the fourth was U, the energy per unit volume in the form of radiation. That was the energy per unit volume. That's something we might want to know. Multiply that by the volume of a box, and you would have the total energy in the form of radiation in it. And the pressure is 1/3 of that. So I'm hoping it jogs your memory that at one point I was saying, oh, look, for radiation, the pressure is 1/3 of the energy density. And this is that again. The pressure is 1/3 of the energy density. Pressure and energy density have the same units because pressure is what per what? What is pressure unit-wise? Pressure is the what per unit what? Not mass. Force per unit area. Pressure is force per unit area, right? And energy density is energy per unit volume, right? But energy, unit-wise, is force times length, right? Because work is force times distance, right? Or F dot dr. So, in other words, energy per unit volume is the same thing as unit-wise. It's not physically the same thing. The same thing as force per unit area, because energy per unit volume, unit-wise, is force times length over length cubed, or in other words, force over length squared. They both have the same units, okay? So the radiation, and this is all a reminder. I could have just kept on going from there, but I wanted to remind you of something you saw before. And now I'm going to preach. You really have to be looking at things and thinking about them, not just when you're in class. If you really want to develop a deep understanding, you have to keep thinking about things. I will say, going to give with the exam, I discovered that a lot of people don't really understand why this is true. Why that was true. Because some people said things like, well, the luminosity is defined to be the area times the flux, and so this is the area and that's the flux. And I'm like, no, that's not how luminosity is defined. How is luminosity defined? A star's luminosity is its what, fundamentally? Power, right, it's total power radiated, right? The total power coming from its entire surface. What are the units of that? What's the units of power? Watts, right, watts. And basically, what I was looking for is for you to realize that I wouldn't even have to tell you this. I could have just said, find an expression for a star's luminosity in terms of its radius and temperature. And then the logic is, okay, well, sigma t to the fourth power, what's that unit-wise? What does it represent? Watts per meter squared, right? That's the number of watts coming out of each square meter of the surface. Whereas 4 pi r squared is the area of the surface, right? Total number of meters squared. So watts is watts per meter squared times meters squared is what I was looking for there. I was really looking for a discussion in terms of, well, fundamentally luminosity is the power radiated out of the whole surface, and so that's going to be the power coming out of each square meter times the number of square meters. So yes. Anyway, okay, continuing onwards. So this means we can now find the derivative of the radiation pressure with respect to radius as follows. Oh, and by the way, here we're assuming that it's thermal radiation, that it's black body radiation. That is perfect thermal radiation. So that's going to say that dp rad dr is going to be equal to 4/3 a cubed, 4/3 a t cubed dt dr, right? In other words, the derivative of t cubed with respect to r by the chain, the derivative of t to the fourth with respect to r by the chain rule is the derivative of t fourth with respect to t, namely 4t cubed times the derivative of t with respect to r. So dp dr is 4/3 a t cubed dt dr. So that four-thirds a t cubed dt dr, right, that's dp rad dr, is equal to the right-hand side, minus kappa bar rho over cf rad. So now just solve for dt dr. dt dr is thus minus 3 over 4ac times kappa bar rho over t cubed times f rad. So now I'm going to draw a picture of I'm inside the star at some distance r from the center, little r from the center. My star has radius capital R, which won't play a direct role in my picture at this moment. And all those little arrows are supposed to represent the luminosity coming out of that radius. Remember last time we were talking about how if you're outside the core, every radius has the same luminosity coming from it. But if you're inside the core where energy is being generated, then the luminosity coming out of any surface is increasing as R increases because energy is being added by each spherical shell. So this is supposed to represent L sub R, the luminosity coming out of that surface of radius R. The radiative flux as a function of little r should be related how to L sub r. So what is flux again? The units of flux are watts per square meter, right? Watts per square meter. L sub r, what's its units? Watts. So F rad, watts per square meter, what am I going to do to LR to turn that from watts into the watts per square meter coming out of that surface? What do I need to know about that surface to get the watts per square meter out of it? The area, right. And what is the area of this shell, of this surface inside the star of radius R? Like any self-respecting sphere, it's 4 pi r squared, right? So F rad as a function of r is L sub r over 4 pi r squared. So we can put that in for F rad here and get our final result. Since F rad is equal to L sub r over 4 pi r squared, we have finally our glorious box-worthy equation. Oh, it's going to be so exciting. Are you as excited as I am? Yes, the tension is very convincing, very convincing. Yes, I'm totally buying it. dTdr, how could you not be excited? I'm excited. dTdr is minus 3 over 4ac kappa bar rho over t cubed times L sub r over 4 pi r squared. Ta-da! Yay, and there was much rejoicing. And this is equation 4a, as opposed to just 4, because this is dTdr when radiation carries the energy. There will be another dTdr for when convection carries the energy outwards, and that'll be equation 4b. That'll be equation 4b. So in other words, in the end, it would be like dTdr equals, and then you do the curly brace thing. In this case, blah. In that case, blue, right? That sort of thing. So here's 4a. The temperature gradient for radiative diffusion transporting the energy. Note that in the outer layers outside the core, where L sub r is constant, L sub r would be sigma Tef to the 4th power, where Tef is the star surface temperature. But this is general for wherever you are inside the star. So I'm going to draw a picture here that should help you visualize what's going on here. And we've already talked about the basic idea, which is that if you're inside the star, don't do this, but if you're inside the star, if you look towards the center, you're seeing hotter and hotter layers, but you can only see so far, right? You can't see all the way to the center. You can, quote unquote, see to an optical depth of 2/3, or in other words, the radiation overall looks like it's coming from the layer. It's got the same effective temperature under our usual assumptions as the actual temperature of the layer at an optical depth of 2/3 away from you. So you look towards the center and you see hotter layers. You look towards the surface and you see cooler layers. It's ferociously hot in there. It doesn't matter. In other words, you know, it's not like you're seeing hot versus cool. It's like, oh my God, hot versus, oh my God, hot, you know. And so there's more energy flowing out than flowing in. But we can now be more specific and say, well, what about kappa bar and rho? Why is it that if kappa bar and or rho increases, that the magnitude of the temperature gradient increases, right? If either of these increase, dTdr in magnitude, there's a minus sign there, but I just care about its magnitude, the magnitude of dTdr increases as well. So let's explain what's going on there. Note that as kappa bar and or rho increases, the temperature gradient required to carry a given flux increases. In other words, let's assume that F rad is fixed here and see what would happen if I increase kappa bar and or rho. Why is it that the temperature gradient in magnitude increases if I increase those things? Why does making the gas harder to see through cause the temperature gradient to have to increase? Because note that if you are outside the core, which is most of the radius of the star, if you're outside the core, L sub r, and thus, well, I should say L sub r is fixed by the rate of energy generation inside the core, right? That's the star's luminosity, and once you're outside the core, every layer has to have that luminosity flowing out of it. And so this is not a free parameter in terms of when you're out in those outer layers. That's determined by the nuclear reactions inside the core. So let's just consider, okay, fix F rad and see what happens when we vary kappa bar and rho. Why should that increase dTdr? So I'm going to draw a picture here. To center of star. It's that away. And here's two layers within the star, namely, and you're in between them. So here's you. Don't do this, right? But there's you inside the star. Here is the direction to the surface of the star. And we'll say that this layer is the one where tau equals 2/3 towards the center from your location. That's a vertical optical depth, the direction towards the center optical depth of 2/3. And on the other side, here's the layer where tau is equal to 2/3 towards the surface. And again, you're really getting radiation from every layer inwards and every layer outwards. But we have this Eddington like approximation derived result that the effective temperature you see is the actual temperature of the layer at an optical depth of 2/3. That's the point here. So the radiation you see, I'll draw some arrows. It's like, here's this radiation coming my way. I can look towards the center. I can look towards the surface. The layer at an optical depth of 2/3 towards the center is hotter than the layer at an optical depth of 2/3 towards the surface. And so that's another way of saying that you see brighter towards the center and dimmer towards the surface because of the fact that the temperature increases inwards. Okay, so what questions do you have so far? Do you understand the setup I'm creating here? So we're looking in, we're looking out. We're really seeing radiation that's a combination of radiation from many, many layers. It's a continuous combination of layers. You see beyond tau equals 2/3, you see closer than tau equals 2/3, but according to those approximations we made earlier, TAF, the effective temperature you see, defined by sigma TEF to the fourth, is the flux that you see. Sigma TEF to the fourth is equal to sigma T to the fourth, where T is the temperature of the layer at an optical depth of 2/3. So looking in towards the center, the outward flux we see, watts per square meter. Outward flux, I'll put a reminder there, because you want to carefully distinguish luminosity from flux and so forth. The flux, watts per square meter, we see from the Eddington-Barbier, or is it Barbier? Barbier, I don't know how to say it. From the Eddington-Barbier relation is F rad out, so that outwards flux right? We're looking at the flux that's coming out towards us when we look towards the center. Why, that's equal to sigma times T evaluated at tau in the inward direction is equal to 2/3 to the 4th power. So in fact, I'll put some, they're not there in my notes, but I'll put little subscripts on my taus in my earlier picture there. Tau in equals 2/3, tau out equals 2/3, optical depth 2/3, looking in towards the center, looking out towards the surface. This is the outwards flux, but this says in because the outward flux is what you see when you look inwards towards the center of the star. Okay? So I'll put that, I had that in my notes. Note that we see outwards flux when looking in. That's why one subscript is out and the other is looking in. We see outwards flux when looking inward! Exclamation point. Okay, does that make sense? What questions do you have? All right. So then we just flip this around, looking out towards the surface. We see F rad in, well, that'll be sigma times T evaluated where? What am I going to put in the parentheses this time? T out, yeah, tau out equals 2/3. To the 4th power, right? And so this thing here, that's TEF looking in, and this one is TEF looking out. Which one's bigger? The top one or the bottom one? Which one's bigger? The top one's bigger, right? Because there has to be a net outward transport of radiation. It's hotter looking in, right? The temperature in the inward direction, the TEF in the inward direction is higher than the TEF in the outward direction. So then I'm going to try to, I'm going to leave this piece right here. So I'll erase around it, but I want to not erase this because I want to be able to like point to it again. So there we are in our protective booth. Okay. The net radiation flux at your location, because of that jerk that beamed you into the middle of the star, at least they gave you a super duper impossible suit that's protecting you. The net radiation flux at your location is then F rad equals, how am I going to get F rad from F rad out and F rad in? What's it going to be? What's that? Not adding them up, because I want the net flux, and if I look in, I've got outward traveling photons. If I look out, I've got inward traveling photons, right? If I'm in a train station and I want to know how many people are getting on the train, and there's 100 people leaving the train and 120 people entering the train, what's the net number of people entering the train?
In minus out.
Yeah, I have to subtract, right? I have to find the difference to get the net. If 100 people walk out of the train and 120 people walk in, the train adds 20 more passengers, right? So here, I'm going to say that it'll be the outward flux minus the inward flux, because that's the net outward transport of energy. So F rad will be F rad out minus F rad in. F rad out's bigger, so there's a net outwards flux. If those two are equal to one another, there'd be no energy transport because just as much energy would be going past you in each direction. But F rad out will be bigger in our star, so that it'll be transporting energy outwards. So that'll be equal to sigma times, fancy curly brace, because I'm using every possible almost kind of parentheses here. I'm just dreaming of how fun it would be to typeset this in LaTeX right now. Aren't you dreaming that too? Wouldn't it be wonderful? Yes. And then you'd be using things like, like backslash left and backslash brace, because you need another backslash because brace is a reserved symbol. And anyway, okay, not really relevant. I just, my mind started drifting at the glory of typesetting this. So, whoops, 2/3, not 3/2. So it'll be sigma times the difference of those t to the 4th power. Right, it'll be sigma times the difference of those temperatures to the 4th power. Not the difference of the temperatures to the 4th power, but the differences of the temperatures of the 4th power, right? If I verbally punctuate, so to speak, or parenthesize or whatever. Okay. So here's the thing. Suppose that kappa bar, I'll wait for you to catch up so you can be listening to me with full attention. Yes?
Is one of those supposed to be out?
It is. Thank you for pointing that out. You've passed my cleverly packaged test. And I have a bridge to sell you as well. Thank you for pointing that out. Yes? Crap. It is. You pass well as well. Yes, thank you for pointing that out. This would look really confusing later if it were like, messed up. Like, because then you're like, wait a minute, I feel like this is wrong, but Dr. Harmon would never make a mistake, would he? So, and then you remember, well, yeah, he would, but yeah. Okay, there we go, all right. If kappa bar were to increase, the gas becomes more opaque, what would happen to the physical distance of the tau equals 2/3 layers from you? If the gas were more opaque, would these layers get closer to you or further from you if the gas were more opaque? They'll squeeze in towards you, right? The harder it is to see through the fog, the closer the tau equals 2/3 layers become to you. But the amount of energy that needs to be transported outwards is not going to change. If you're trying to get that energy from the core to flow out to the surface, you've got a fixed budget, so to speak. And so that's not subject to change, but what is subject to change is how close those layers are to you because of a different opacity. But the temperatures need to pretty much stay the same because you need to have the same amount of net outward transport of energy. So in other words, if the opacity were to become greater, the same temperature difference would have to happen over a smaller physical distance. The same temperature difference would be needed over a smaller physical distance, which would mean dTdr was larger when the opacity was larger. And that's the crux of the argument here. The harder it is to see through the gas, the closer those layers become to you, the temperature needs to change more rapidly with distance, therefore, physical distance, therefore, in order to transport that given amount of energy that you're needing to transport to the surface. Let's write all that down, shall we? But I wanted to say the argument first and use my hands and all that sort of thing before writing this all out here. If kappa bar and or rho increases, you can't see in or out as far. I guess we'll say you can't see as far in or out. The tau equals 2/3 layers are closer to you, in parentheses. And so, if dTdr, and I didn't say this before, so this is something I'm adding. If dTdr somehow did not change, this is the counterfactual. Suppose, let's suppose, well, it got more opaque, but dTdr stayed the same. If dTdr somehow did not change, it did, but let's pretend it didn't. What am I going to say? The difference in well, let me put it this way. I'm going to write a slightly different thing than I have in my notes. If it did not change, then that whole business of inside the curly braces part, T of tau, which one is it? Tau in equals 2/3. I could have figured it out, but too much pressure. Then T of tau in equals 2/3 minus T, that minus, no, where do I want this? T to the 4th for tau in equals 2/3. And I could have put it outside the whole thing too, but I'll just put it next to the T. T to the 4th for, I don't need the extra square bracket. Okay. Okay. I'll do it like this. T of tau in equals 2/3 all to the 4th power, like I did over there, now I realize, okay, minus T of tau out equals 2/3 to the 4th power. If the temperature gradient didn't change, if dTdr didn't change, and I bring the surfaces closer to me, would those surfaces now be, in this case, would this difference be bigger or smaller than it was before? In other words, if I am looking in and that surface comes closer to me, what happens to the temperature of that surface? If the temperature gradient's the same, but now I can see closer to me than I could before, what happens to the temperature that I'm seeing, the TEF that I'm seeing? It decreases, right? Because I'm seeing closer to me where the temperature isn't as large as it is further from me. So bring this layer in, it's closer to the temperature where I am instead of further away where it's hotter. Similarly, when I look out, the temperature now gets hotter that I can see because the temperature's decreasing that a ways. And so if the layer gets closer to me, it looks hotter than it was before. And the difference between them has gotten smaller as a result of that. They're closer to me, so there's not a big a temperature difference anymore. So then, I should say, then, blah, 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 the difference in those temperatures to the fourth power would be smaller than before. Would be smaller than before. So F rad would be decreased. F rad would be decreased if the temperature gradient didn't change. But that can't be allowed because I have this fixed budget. I have to transport the energy being made in the core outwards, and that's not negotiable. So in other words, this can't happen. The temperature gradient will have to increase in order to maintain that same outward flux of energy. So thus, in order to carry the given, right, because we said, let's assume that F rad is fixed. The given flux F rad dTdr will need to increase. We'll need those layers to be hotter and cooler than if the temperature gradient didn't decrease, if it didn't change, in order to carry that flux. dTdr will need to increase compared to before. If kappa bar and or rho increases, all else being constant. If F rad stays constant and everything else stays constant except kappa bar or rho increases, then you're going to need dTdr to be larger because keeping it the same would decrease the flux. So it's going to need to be larger so that essentially that tau equals 2/3 layer wouldn't necessarily be the case. The difference is what matters, but roughly speaking, that tau equals 2/3 layer has to have the same temperature now that it did before when it was further away. So that means that that difference in temperatures is taking place over a smaller physical distance. dTdr has to have gotten larger in order to keep carrying the flux. That's the argument. What questions do you have? Because I might ask you to explain that.
Could you explain that again?
Okay, so, all right. So I'll just kind of start from the top here, all right? The flux we see is because the tau equals 2/3 in layer is hotter than the tau equals 2/3 out layer. So Tef inwards is larger than Tef outwards, so there's a net transport of energy. That's kind of step one. That's why there's flux coming through in the first place, a net flux, okay? All right, so now let's suppose I keep FRAD constant, but I dial up the opacity. How do you do this? I don't know, I'm just doing it. I have a knob, I'm dialing up the opacity, all right? Can't see as far through the gas, and so the tau equals 2/3 in and out layers both get closer to me, all right? Now, the temperature gradient is how fast temperature changes with distance away from me. And so if the temperature gradient stayed the same, but those surfaces got closer to me, then their difference in temperatures would be smaller than before. Because if they were right on top of me, they're at the same temperature. The further they are away from me, the bigger is their temperature difference. So if I don't change the derivative of the temperature, the closer they are to me, the closer they are in temperature to one another. Okay? But if that happened, I wouldn't see as big a difference in their temperatures anymore. Not as much flux would be carrying. There wouldn't be as big an FRAD as before if dTdr did not change. But I'm assuming that FRAD is staying constant, that changing the opacity isn't changing FRAD, which it won't because I have to carry the energy coming up from the core, right? So how do we resolve this dilemma? We resolve it by saying, well, the dTdr had to get bigger so that temperature varies more rapidly with distance away from me, so that in that narrower range now, I'm still getting essentially that same temperature difference as before, so that it's looking just as hot as it did before looking inwards. It's looking just as cool as it did before looking inwards. So that's why the temperature gradient has to get bigger. Okay? That's the idea here. Questions, comments, observations?
So the closer those layers are to you, the faster dTdr changes.
Assuming for a given temperature difference between them, yeah. So it's not dTdr, it's T itself that's changing, right? So in other words, put it another way. Suppose you just said, here's these two layers, and I know their temperatures, okay? And dTdr is how fast temperature changes with distance. And so really, it's the limit as dr goes to 0, blah, 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 whatever. An approximation is change in temperature over change in distance is the derivative of the temperature, right? So let's say this hand is at, let's see, body temperature is what, like 37 Celsius, right, roughly? This hand is at 40 Celsius, and this hand is at 35 Celsius, okay? And they're going to stay that way, all right? So delta T is 5 Celsius between my hands, and imagine that they're surrounded by stuff that's smoothly varying between their two temperatures, right? So now they're about, about 2 meters apart is my wingspan roughly, okay? So now the temperature gradient is 5 degrees Celsius, or Kelvin for that matter, 5 Kelvin per 2 meters, all right? Ooh, I bring them closer together, okay? Now it's 5 Kelvin per 0.25 meters, right? It got bigger, the gradient got bigger because the same temperature difference happens over a smaller physical distance. And that's what would be happening here, is if we're carrying the same flux, then again, details, it might be the temperature's changed a little bit, but the difference in the T to the force has to stay the same in order to carry the same amount of flux. And so the temperature needs to change more rapidly with distance in order to bring that about. If the opacity increases, ta-da, or the density, because they both are in the, both of them make it harder to see through the gas, basically. Okay? That's the argument there. And I think it is indeed, drive, go away, drive, be musical. You must drive. I don't know. I think it's the witching hour now, so let's do this. Okay, so, blah, 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 blah. All right. I've been kind of saying this over and over again, but let's put this in the notes, this idea that FRAD's not a free parameter. You don't just get to change it willy-nilly, as it were. I think I pushed the button, didn't I? I have to look. What's that? Is it going blink, blink, blink? Oh, okay, cool. All right, yeah. Note that outside an energy generating, note that outside an energy generating region, note that outside energy generating regions, and I'm not saying the core because there are stages of a star's evolution where the core isn't generating energy particularly. It's inert. It might be slowly gravitationally contracting, but anyway, outside energy generating regions. So in other words, in regions where epsilon is equal to 0, we have to transport the luminosity coming up from the core or fusing shells. I'll just say, in my notes I say the core, I'll say from the central regions to be general. We have to we have to, where am I? We have to transport the luminosity coming up from these central regions. So FRAD is not a free parameter. We don't get to just change it. We have this criterion that no, FRAD needs to be whatever it needs to be. It's L sub r over 4 pi r squared, whatever r you're at. FRAD is LR over 4 pi r squared is not a free parameter. It's not something we can just play around with. Exclamation point. Right, that was part of the argument too, is that you don't get to just change it however you like. Star's got to do what a star's got to do. It's got to support itself against its own weight. And then you don't have to write this, you've already got it in your notes, but I just want to put it here just to refer to it. The equation 4a was dTdr was minus 3 over 4ac kappa bar rho over t cubed L sub r over 4 pi r squared. Excuse me. By the way, quickie, why is there a minus sign there? What's that represent? No, this minus sign right here. This is kappa bar right there. Why is there a minus sign in the expression for dTdr? What's the minus sign telling you physically?
As you get further from the center, the temperature is lower.
Yeah, it's just saying the temperature gradient's negative, right? That it's decreasing with distance from the center. So, so there's the equation. You've already got it in your notes. Don't copy it again. You've already got it. My point is, now I can point to that and say, note that as T increases, the temperature gradient required to carry the flux decreases, right? As T cubed goes up, the temperature gradient that you need goes down. Note too, because we just noted something over there, that as T increases, the magnitude of dTdr needed to carry the flux decreases. And so why is that? Well, I mean, one answer would be because it's 1 over t cubed there. Okay, I know, right? But why physically is that the case? This is simply because it is the difference in t to the 4th between the inwards and outward directions that matters. It is the difference in t to the 4th in the inward and outward directions that matters. And so really, in terms of the flux, what you're really doing is taking the rate of change of t to the 4th. And so what's really relevant is dt to the 4th dr, the derivative of t to the 4th. What's dt to the 4th dr? You already used it earlier. What's the derivative of t to the 4th with respect to r from the chain rule in terms of dt dr? What's the derivative of t to the 4th with respect to r?
4t cubed. No, nothing.
It's 4t cubed times dt dr, right? From the chain rule, right? dt to the 4th dr is dt to the 4th dt dr. So it's 4t cubed dt dr. dt to the 4th dr is 4t cubed dt dr. So that says that the thing that we really care about, t to the 4th, that changes faster with distance as the temperature increases. So dt to the 4th dr, I'm sorry, stop it. So t to the 4th changes faster with respect to r. For a given value of dt dr. As t increases. So in other words, so to speak, a given temperature gradient becomes more effective at transporting flux as the temperature increases. And so that means that remember, we divided through by t cubed, and it's just reflecting that fact that how much dt dr, how much dt dr you need, so to speak, to carry the flux gets smaller because of the fact that as the temperature increases, a given dt dr would carry more flux. So you don't need as much dt dr to carry the given flux if the temperature is higher, is the idea here. dt dr needed to carry the flux decreases as t increases because a given dt dr would carry more flux as temperature increases. So you don't need as much dt dr when the temperature increases. So a given temperature gradient will carry more flux as t increases, or if you have a certain flux you need to carry, dt dr will get smaller if the temperature increases. But then this is saying something very important, which is taking us to our next adventure. We're going to get all bubbly soon. So as we approach the surface, What's happening to T as we approach the surface? Is it rising or falling as we approach the surface? It's falling as we approach the surface. T keeps decreasing. Tending to make dTdr larger. But as we will now see, and we're going to be doing it joyfully, as we will now joyfully see, large, I'm going to put I should put absolute value signs around there because it's negative, so you know, I'm talking about its magnitude. Large dTdr in magnitude tends to favor convection. This is why the sun's outer layers are convective. Thus giving DH a job. Thinking about myself here, because those of you who know anything about star spots know that strong magnetic fields suppress convection, causing that region to become cooler and thus darker than the rest of the stellar surface. So I need the sun's outer layers to be convective in order to carry out my research program. So it's all about me. Yes?
Use this to explain why I think you've said before that like massive stars, the inner layers are convective.
So yeah, it's part of it. So a more massive star, it's just hotter throughout, right? And so its surface layers on some level, right, they don't get down to the point where convection is favored. And so their outer layers don't become convective as a result of that. But their cores are convective, it turns out, because they fuse hydrogen via the CNO cycle, which is extremely temperature dependent, such that in that case, radiation couldn't carry the gradient and convection takes over in them. But in terms of the outer layers, how come massive main sequence stars don't have spots? Yeah, because their outer layers are too hot for convection to be favored. They transport energy radiatively all the way out to the surface. Yep. So again, it's all about me and my research program. Yes. All right. And you know, as I always say, my humility is one of my many outstanding qualities, right? The universe is doing this just for me. Because I couldn't possibly find another program if there was like, you know, well, actually, the changes in the laws of physics that would make this not happen would also probably make the universe incompatible with humans too, right? You know, you'd have to be changing fundamental constants and so forth. So, so it's about all of us. The universe has got the right laws of physics. The same laws of physics that make the outer layers of low mass stars convective favor the evolution of human life, essentially. But many other things do too, it's not just that. All right, anyway, yeah, stars are convective, therefore I am, as the great philosopher Descartes once said. So our low mass stars' outer layers are convective, therefore I am. Yes, right. Yeah, that needs to be on the right. The outer layers of low mass stars are convective. That's not something I plan to say today. Therefore, I am. I forget, is it Rene with 2 E's or?
It's one with the, I think.
Yeah, that, right, that, right, like Ren, like that, Rene. Descartes, right? Rene Descartes.
The performance version.
As told by DH, yes. There we go. Yes. Did I spell Descartes correctly? I think so, right. And you remember, right, as physicists, mathematicians, what's an all the time use we have for his name? Cartesian coordinates, right, are named after Rene Descartes because, you remember the story? He was in his bedroom, I think it was, and he heard a fly buzzing, and he noticed that it was flying around, and it dawned on him that you could specify the fly's location in the room by how far it was from each wall and the floor, right, 2 walls in the floor, and that made him think of, oh, a Cartesian coordinate system, and thus history. So a little fly is responsible for, well, with help from a human brain, is responsible for Cartesian coordinates. And of course, you've taken the multivariable calculus. So the fly's path would be a parameterized curve, where t is the parameter that specifies its 3 coordinates as a function of time. Ah, lovely. Anyway, okay. So let's talk about the condition for convection. When will convection occur? And because I like weather, we'll also tie it to things like our own atmosphere, for example, as well, right? Okay, so we'll eventually do that. Condition for convection. We're going to get this condition under which convection occurs. Maybe I'll do a spoiler alert, just to give you a sense of, like, because it'll be a bit of a long voyage, and so maybe it shouldn't be like where you're starting out on the path and the tour guide doesn't tell you where you're going, and so you don't know, why am I on this path, right? Am I going to see a castle? Am I going to see, what am I going to see, right? And here it is. And you're there, it's like, the backpack that somebody lost last year. Well, okay, now let's get on the bus, everyone, right? So the condition for convection, where this is eventually going to get us is equation 4b, right? So get excited. It's going to be that, well, I want the condition here. Let's see. Yeah, that the derivative of the logarithm of the pressure with respect to the derivative of the logarithm of the temperature is less than or equal to gamma over gamma minus 1, where gamma is equal to Cp over Cv, or in other words, the specific heat at constant pressure divided by the specific heat at constant volume. So that's where we're eventually headed with this, and we're going to discover that in this case, our equation 4b, spoiler alert, is that the temperature gradient for adiabatic convection, as opposed to radiative diffusion, is equal to minus, there it is, that sound again, minus the quantity 1 minus 1 over gamma, that same ratio of specific heats, times mu mh over this Boltzmann constant times g times the mass interior to radius r over r squared. That's going to be equation 4b, where mu is the mean molecular weight. Equals average mass per particle. So we ain't there yet, but I figure giving you those equations will get you excited. I mean, look, doesn't that look glorious that we're going to do? Oh my gosh. Yes?
What does it say on the top right, specific heat
At constant pressure.
and the bottom one?
Constant volume. So that's why it's Cp over Cv. So specific heat at constant pressure, specific heat at constant volume. Have y'all met like the specific heat at constant pressure versus the specific heat at constant volume? So specific heat at constant volume is like if you have a bunch of material and it's trapped inside a container, the question is how much heat do you have to put in to raise the temperature by 1 Kelvin? Whereas at constant pressure, you open the container up to the room, and so, well, you don't open the, it'll expand. You have it like, one example is you have the container, but at the top is a movable piston. And so you put in heat, and the piston can rise as the pressure rises to keep the pressure inside the same as on the outside. And so then you've got the specific heat at constant pressure, which is always bigger than the specific heat at constant volume, because if it's a constant pressure, you're allowing the gas to expand and do work on its surroundings. So some of the heat you put in raises its temperature, but some of it does pressure volume work on the surroundings. And we're going to be talking about that in detail here. And so there's a specific heat at constant pressure, a specific heat at constant volume, and it turns out that ratio gamma shows up in those equations there. Fun with thermo. This is going to be some glorious thermo that we're doing here. And I'm not seeing enough happiness. Yes, that's right. I want happiness about this. I want you to be happy if it kills you. No, I don't want that. Because why would I want to teach with no students, right? I mean, come on. So, all right. So we're going to draw us a pretty picture here. Here we have, and this is based on a similar diagram in your book, it's a bubble. It's a blob of gas, a bubble of gas that, for whatever reason, starts rising upwards. So there's gas everywhere. Gas, 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 gas. A bubble of the gas. Some little packet of it. There's a bubble of the gas, and for whatever reason, it starts rising upward. We're going to look for the condition that it will be buoyant and continue to rise upwards. And if that happens, if a rising bubble of gas stays buoyant, that's when convection will happen, because that will favor blobs of gas rising upwards. Whereas if it doesn't stay buoyant, if it says, oh, no, I'm actually heavier than my surroundings, it'll come right back down again instead of continuing to rise. So here's our bubble of the gas, and it has P initial of B, the bubble. So there's its initial pressure, and it has T sub I of the bubble, its initial temperature, and it has rho, the density sub I of the bubble, its initial density. And I know Kathleen's going to say, what does that? So capital P sub I parentheses B, capital T sub I parentheses B, capital rho sub I parentheses B. So T sub I parentheses B, where B stands for bubble. Yes, T sub I, P sub I, rho sub I, all of the bubble. So it's not as a function of bubble, It just, right, it just means of the bubble here. That's, hey, it's the book's notation. I didn't come up with it. Give me a break. You know, it would be fun, wouldn't it? Yes, all right. And then up here, it has risen some distance dr, expanding against its surroundings because the pressure is falling outside of it, and so it's expanding as a result to keep its pressure the same as inside. And so up here, it has P sub F of the bubble, T sub F of the bubble, rho sub F of the bubble. And next to it, we write for the surroundings, the rest of the gas. Why, up here at the bubble's new location, we have the final pressure that the bubble feels from the surroundings, and the final temperature of the surroundings of the bubble. That's what the S stands for. As a function of surroundings. No, it's not. It's not. It just means of the surroundings. And the density of the surroundings, rho F, of where the bubble finds itself after having risen a small distance dr. And of course, down here, it started out surrounded by gas with Pi of the surroundings, Ti of the surroundings, rho I of the surroundings. All of those good things. Okay, so to set the stage, I said it already, but let's put it in the notes. Consider a bubble. That's why I said we were going to get bubbly. Consider a bubble of gas. For our star, it's liable to be plasma, embedded in surrounding gas and imagine the bubble begins to rise for whatever reason. Imagine that for some reason the bubble begins to rise. And while I don't put it this way in my notes, I'll do a spoiler alert here. Convection happens if a rising bubble stays hotter than its surroundings and as a result remains buoyant. That's what we'll need. It needs to be buoyant. It will need its density to be less than the density of its surroundings, and that will make it buoyant, and then it'll keep on rising. Actually, I should say, stop, hotter and less dense. I mean, the two go together, but I'll just throw that in here. Hotter and less dense than its surroundings. And as a result, remains buoyant, so it keeps on rising. if that condition holds for a layer of gas, it's unstable to convection. We live in the troposphere of Earth, the layer of the atmosphere where this holds. And this is why you can have birds soaring on thermals. Thermals is rising convective air that they catch with their wings, and it props them up. It's why we have pretty puffy cumulus clouds, cotton ball clouds, because convection, if you ever watch them grow, that's convection. As they grow, air is convecting upwards, cooling as it does so, and under the right conditions, water vapor condenses out and makes the cloud. That's what you're seeing in those conditions. Meanwhile, planes fly in the stratosphere. And the stratosphere is a layer where temperature rises with height because of the presence of ozone, absorbing ultraviolet light from the sun. And if temperature rises with height, you won't get convection because as a bubble rises, it's doing work on its surroundings, so it's automatically true the rising bubble is cooling off as it rises. But it needs to be staying hotter than its surroundings, and if its surroundings are getting hotter the higher you go, and the bubble is cooling off the higher it goes, there's no way it's going to stay hotter than its surroundings, so you don't get convection in the stratosphere. But in the troposphere, you can have a situation where the bubble's cooling off, it's moving into cooler regions, but if the outside is cooling off as with altitude faster than the bubble is, it can stay hotter than its surroundings and remain buoyant. Why do planes fly in the stratosphere? Because it's stable to convection. You don't get convection in the stratosphere, and so you're not likely to get turbulence, buffeting, and so forth. If you're flying along and you're in the stratosphere, that's why planes fly in the stratosphere, both because the air is less dense there, and so it's more fuel efficient, less air drag, but also because of the stability to convection. Sometimes, though, you still get a bumpy ride, and that's because if the troposphere is especially convective, you can get a convective bubble that, from its momentum, pushes into the stratosphere, and then the plane can get buffeted by it, either from below going up or from above going down when the gas sinks back down again. And you get, oh, fasten your seatbelts, we're about to hit turbulence. But when you're in the troposphere flying in for a landing, you're more likely to just naturally be doing this because you're moving through convective upwellings and downwellings of air. See? Whoever said what you learn in astrophysics can't be applied to your everyday life? Right there, okay? All right, so continuing here. At all times, the bubble, the pressure inside and outside the bubble are the same. That's a really good approximation. The bubble has to remain at the same pressure as its surroundings. So as the bubble rises, the pressure outside is falling because pressure decreases with height in both a star and in our atmosphere. So the pressure outside is decreasing, and the bubble's pressure has to decrease at exactly the same rate as it rises, because what would happen if the bubble were at higher pressure than the surrounding air or gas or whatever? It would expand. And what would that do to its pressure? It would make it fall. So in other words, what's going to happen is that the bubble will expand in just the right rate to keep the pressure inside and outside equal, because if there was any significant difference, if it was lower than outside, it would squeeze until it was equalized. If it was higher than outside, it would expand until it was equalized. Now, if this happened very quickly, the bubble would oscillate, it would ring, it would like overshoot the equilibrium. But the bubble's rising slowly enough, it's true. The bubble rises slowly enough that it just kind of keeps pace with the outside pressure, is what it comes down to. The pressure inside and outside stays the same because any difference will be quickly equalized. any difference will be quickly equalized. The time to equalize is short compared to the time scale over which the pressure outside is changing. If the bubble were at higher pressure, it would expand to lower its pressure and vice versa. It would expand and lower its pressure and vice versa. So as the bubble rises, the pressure stays equal to the outside pressure. And our cute little bubble should start out with the bubble values equal to the surrounding values, because it's a little piece of blob of gas in those surroundings. So when it starts out, it should have essentially the same conditions as the surroundings. Now, it can't be exactly the same, because then there'd be no particular reason for it to start rising. But it ought to be at essentially the same conditions inside and outside. Initially, T and rho, because we know P is the same, T and rho of the bubble, T and rho of the bubble are essentially the same as those of the surroundings. But as it rises, T and rho begin to differ from the surrounding values. And that's the key here, because the question will be, does rho stay smaller than outside, or does it get bigger than outside? And that's all the difference from the surrounding values. And now, because of the way my brain works, I have this vision in my head of, we make a balloon that's shaped like a good old boy, and it's a rising bubba. Sorry. Okay, so anyway, differ from the surrounding values. So, heat conduction is inefficient in a gas, and so as a result, in like physics 1, maybe 11 or whatever, you do some thermodynamics where you talked about like dq, heat transferred, right? All that kind of good stuff, or for that matter, how many of you took have you taken thermal yet? I don't remember. You're like, okay, but you still saw like dq, right, and all that kind of stuff, right? Heat conduction, excuse me, is inefficient, so we can assume that there's no heat flow in or out of the bubble as it's rising. And we call that an adiabatic expansion of the bubble as it rises. Technically, it means that the entropy of the bubble stays constant as it rises. Did you talk about entropy at all? Yeah, it won't be super crucial here. I'll put it here so that in the future you look back on your notes and it'll say, oh yeah, the entropy, that's making sense now, right? Okay. I didn't believe in entropy until I took statistical mechanics. It just sounded like total made up BS to me. And then I took statistical mechanics and discovered its actual definition. I'm like, I believe in entropy! I mean, I knew it was right before, right? I didn't think everybody was making it up, but I was just like, what is it? And, I was like, oh, well, it's disorder, blah, blah, blah. Yeah, but what is it? And then I finally learned what it was, and I'm like, my life is different now, different and better, that I understand what entropy actually is. So look forward to that. Anyway, begin to differ from the surrounding values. Where am I? Because heat conduction is inefficient. Over the short time scale in which a bubble rises, we can assume that it does so adiabatically, i.e. with no heat flow into or out of the bubble. Because heat conduction is inefficient, over the short time scale in which a bubble rises, we can assume that it does so adiabatically. Adiabatically. i.e. with no heat flow into or out of the bubble. In other words, with no heat flow into or out of the bubble. And that means any temperature change is only due to the work it's doing on its surroundings or that the surroundings are doing on it. Because you can reverse all this. You can also, you can turn everything around and say, well, what happens to a sinking bubble? Does it stay heavier than its surroundings? So this works for rising bubbles and sinking bubbles. You just kind of turn everything around. With no heat flow into or out of the bubble. Okay, so here's where I'll write something that may not mean much to you now, but later, someday, you're going to learn about entropy, and you're going to be like, you know what, we talked about adiabatic convection back in astrophysics, and with my burning passion to keep up with my astrophysics knowledge, I'm going to go read that bit about entropy in there, and it's going to make sense to me now. Since dq equals TdS, where S is the entropy, dq is TdS equals 0, an adiabatic process can also be described as one that takes place at constant entropy. The entropy of the gas stays constant as the bubble rises or falls. So I'm verifying, right? So you didn't see dq as TdS anywhere, is that true? Or did you and you just forgot? No, you don't remember that. Okay, yeah. So again, it's not going to be crucial to our development, so that's okay. It can also be described as one that takes place at constant entropy. Constant entropy. All right. You know, this is just ideal because I'm going to get to this point here, and then it'll be time to stop, and then it'll be a long time before we come back to this. And so I'll be like, so y'all remember what we were doing last we met? And you'll be like, no. Except that's not going to be true because you're going to review your notes. That's right. Your passion to learn this is going to cause you to review your notes before next we meet. And in fact, you might have even read ahead in the notes and you'll be like telling me what I'm going to write next. Yeah. So.
Because we don't have any homework this week.
Because you don't have any homework, so you should be otherwise occupied, right? Exactly. The quality time you could have spent doing homework can be quality time reviewing, previewing notes, and so forth. Yes. Uh-huh. Yes. Okay. Here's another paragraph. The constraint that the bubble rises adiabatically is what causes rho and T inside the bubble to differ from the surrounding values. I'm going to say, hi, Kyle or Dr. Trees or Dr. Ding or Ms. Storms in there, because I'm hearing things there. The constraint that the bubble rises adiabatically is what causes rho and T inside the bubble, because the surroundings, the entropy is different at different heights in general, but the bubble's entropy stays constant. But again, that's not crucial to understand it in those terms. We can also understand it in terms of as the bubble rises, it's doing work on its surroundings. That's the only thing causing its temperature to change, and its temperature will generally change more or less than the surroundings do as it's rising. It's finding itself in surroundings where the surroundings are now either hotter than it is or cooler than it is, and that's what determines whether it keeps on rising or not. The constraint that the bubble raises adiabatically is what causes rho and T inside the buble, inside the bubble, to differ from surrounding values. The bubble's temperature change, since there's no heat flower in and out, comes entirely from I'll call it PDV work, right? Did you do that where the work is PDV, that business, right? Comes from PDV work that the bubble does on its surroundings. That's the only thing that's changing its internal energy per kilogram. And its delta T, in general, stop it. In general, it's saying it's past time. You should stop. In general, won't be the same as for the surroundings. And again, the surroundings are just like we're considering them to be like just sitting there static, and it's finding itself in new surroundings. Won't be the same as for the surroundings. And the idea is that P is, as we'll see, rho KT over mu MH. Oh, I didn't say before, MH is the mass of a hydrogen atom. I hadn't written that before. Rho K2, this is a version of the ideal gas law. Right? So if P stays the same, and it does, then rho T is the same as outside. If mu is, and that'll be important because because mu can be changing in the bubble if we're in an ionization zone. We'll see that the mean molecular weight, the average mass per particle, if things are becoming less ionized, there's not as many electrons around, and they're very light, and so the molecular weight starts to change as a result of that. But anyway, then rho T is the same as outside if mu is. So if T of our bubble is greater than T of the surroundings, then rho of our bubble, I'm putting sort of, what do I want? If T of the bubble is greater than that of surroundings, then rho of the bubble will be less than that of the surroundings, because if rho T is the same for both, then if T is bigger inside the bubble, rho is smaller inside the bubble, and it stays buoyant. So that's why if the bubble stays hotter than its surroundings, it stays buoyant. It keeps on rising. It's convection time, convection party, woo! Yes. So go have a nice break, and you'll have maybe turkey or tofu or something made in a convection oven. And you'll be thinking, wow, convection. Yes, we get to go back to this after break talking more about convection. How awesome is that? Yes. Woo! Woo! Yeah. Yeah. Yes. It'll be cumulative, yes. Yes, yeah. But I will give you a review guide again, yes.
Everyone's giving us review guidance, but that's like, you only have like 5 days to study.
Yeah, well, I can produce it soon, and then, yes. I can give you, yeah. So after, so tell you what, after I'm done grading the exam, which will be soon, I will post final exam review guide, and then I'll start grading the last homework. So I'll put it in that order.
Don't rush.
Don't rush, don't rush. But yeah, so that'll be the story there, so that you have plenty of quality time to enjoy.
I already told my parents, I'm like, y'all better be ready for me to be teaching you my entire class.
Nice, nice, very good, excellent. I like it. Yep. You'd be like, they get like even more out of tuition dollars, because they too get a college education out of their tuition dollars. Yes.